the last person I saw, the last place I visited was McGill and you a year ago, and plus 5 days or something like that. So it's nice to return the favor. Too bad you can't come in person. So so Thomas is actually a U of T alumni. He did his undergraduate degree at U of T and worked with Peter MacDonald at UT Mississauga in chemistry. He went on and did a master's degree at Western with Sylvia Mittler, and then did his PhD with Ruth Signorell at University of British Columbia, looking at radiation and particles there. And then he moved on to the UK and did a postdoc with at Bristol, looking at single aerosol particles as well with Jonathan Reed. So he's been at McGill for the last 6, almost 7 years, I think, where he set up a really fantastic lab, great equipment, and lots of great students. And he's going to share some of his work with us today. So welcome, Thomas, and take it away.
Thanks. Let me just share this. So hopefully that's appearing okay. After, does that look good, or
yeah, that looks good, thanks.
Okay, great, thanks. So yeah, I can't seem to go into full screen, but nevertheless, I'll persevere. So yeah, I'll be talking today about optical trapping and spectroscopy of single aerosol particles, work in my lab over the last few years. So just some background. I won't give the typical, I guess, aerosol introduction, but I will give the introduction relating to aerosol single particle measurements. And that is that optical tweezers are a tool that can be used to trap and hold single aerosol particles. So here on the left, we can see a focused laser beam, and maybe can everyone see my cursor? And again, never used Teams before, so hopefully that's showing up. But anyway, we see a focused laser beam, and that can be used to trap and hold a single droplet, like we see the image on the right here, where we have a micron-sized droplet that's being held in the aerosol optical tweezers. As my daughter enters the room. So here, what we can do is, with this tool, is trap and hold a single aerosol particle. Just a second. Woke up from her nap. And the animation on the right is just showing a plume of aerosol going by, and then one being held with the optical tweezers there. So we're just imaging in the focal plane here with this setup. So what you can do is build an entire instrument around this. So that's what the diagram is showing. This instrument is actually commercially available. The basic idea is you just have a trapping cell where you want to control the environmental conditions to, ideally to simulate what would take place in the atmosphere. And then you trap a single aerosol particle, and then your experiment is you're, say, adjusting the relative humidity, and you observe what happens with the droplet that you've trapped, or the particle that you've trapped. So here the whole setup itself is essentially an inverted microscope. So you have your trapping laser going down, the highlighted path, and then you can image the droplet like I was showing on that last video, just with a simple LED and then just a CMOS camera at the back end here. But that's not really useful aside from just verifying that you've actually trapped something, because all you can see is, very crude size changes, and that's about it. However, what is useful, and the primary tool we use, is inelastic light scattering, specifically Raman scattering. So because you've trapped a droplet in this focused laser beam, you get a lot. It's in this intense laser field, so you get a lot of Raman scattering, and that's what we collect on the spectrograph down this channel here. So the back scattered Raman light in this case here. And when you do that, what you see is something quite interesting. So here's the Raman spectra for a water droplet, just an aqueous droplet, in the region of these stretching modes for water. So water itself is a very weak Raman scatterer. And what you see, if you just had, say, bulk water, so a glass of water, and you took the Raman spectra, what you'd find is you just get this broad band back like this. So very indistinct, from like 3200 to 3700 wave numbers. Again, very weak effect. However, when you trap this droplet, you get these sharp spikes in your spectra. So the most noticeable feature of this Raman spectra here, happening at these different wavelengths. And the origin of this effect is the droplet that you've trapped can actually act as this high quality factor optical cavity. And that cavity will have certain characteristic modes, and those show up in the Raman spectra, because you have Raman light that's scattering at all these different wavelengths. And whenever one of those matches up with one of these modes, you get enhancement of that scattering at that specific wavelength. And this is called cavity enhanced Raman scattering, and the spectroscopy associated with it is called CERS, or cavity enhanced Raman spectroscopy. This is going to be the main tool that we're going to use, or I'll use, describe throughout this presentation to do our measurements. And what you would like to, or if you want to actually get useful information out from these measurements, what you need is some sort of model that describes how this cavity behaves in terms of size and refractive index and how these modes shift around. So for just a homogeneous sphere, so something that's spherical and has uniform composition, we have, of course, the famous Mie theory. This describes how a plane wave interacts with a homogeneous sphere, over 100 years old now. And of course, Gustav Mie famously explained the color of colloidal gold nanoparticles. And I won't go into that particular experiment, but nevertheless, we can look at his solution to the scattering problem. Or his approach, I guess, in the modern mathematical physics language would be to expand the fields using vector spherical wave functions. And this type of problem is what you're trying to do here is you have your scattered field, your ES, and then you have these unknown coefficients. Those are the only things you don't know. And you have your incident plane wave in Mie's case. And you completely know that. And so you just apply the boundary conditions from Maxwell's equations to this problem. And then you can, after some a bunch of orthogonality relationships, you can get out your scattering coefficients here, the famous Mie coefficients. And what's interesting about these coefficients, and what was noted by Peter Debye, who solved this problem independently and published his work a year later, was that when the denominators go to zero, you have a resonance. And this is going to lead to the origin of those spikes that I showed in that spectra before. So these two equations here from these Mie that you can get out of these Mie coefficients, they're going to give us our resonance condition. So you can just combine those together with one concise equation here that this will just tell you all about the electromagnetic modes inside the droplet or your spherical homogeneous particle. Okay, so if you just look, this equation has an infinite number of solutions. If you look at the first 4 solutions for each different polarization, you don't find much that's remarkable. So you just have basically, as you go to higher mode number here, so that's what the 1, 2, 3, and 4 are indicating mode number. You just see that the size of the sphere relative to the wavelength is becoming larger. Sort of see that here. But in all these cases, it just looks like the sphere is sort of focusing the light. This is just the norm of the electric field that I've plotted. So nothing that interesting. When you go to very high wave mode number, what starts to happen, so now the sphere is becoming much larger relative to the wavelength of light, is the field itself becomes localized just inside the surface of the sphere. So here we are at the end at TE 50, so mode number 50. You see that strong, intense field just inside the surface. And that's the effect that actually leads to the phenomenon that in the spectra that we observed. So these modes where they're light strongly localized just inside the surface of the sphere are called whispering gallery modes. So here's an example plotted for TE 44. And they can actually be understood within the realm of geometric optics as well, because you can just think of it as light's just traveling around inside through total internal reflection. And if the wavelength of light is just correct, after it circulates one round just inside the sphere, it'll constructively interfere and build up. So that's why it's very sensitive to the size of the sphere. And whispering, the reason why the name is whispering gallery is because there's, of course, an analogous phenomenon that was studied much earlier in acoustics, where St. Paul's Cathedral in the UK, where there's this dome roof where you can go up to this dome. Well, normally you can, but it's probably closed now. But even if you go under normal circumstances, it's usually pretty crowded. But nevertheless, there's this whispering gallery up there where you can hear someone whisper on the opposite side. And that's the same basic physical principle, where you have an acoustic wave traveling around and certain frequencies will constructively interfere and build up. So that's how you're able to hear them. Now we're dealing with electromagnetic waves, not mechanical waves, in a much different size scale. Nevertheless, it's the same basic idea of constructive interference. And as I was saying, they're very sensitive to size and composition. So if you just change the size or refractive index a very tiny amount, you'll be off resonance, and then the droplet just acts as a lens, basically, which isn't that interesting for any application. So you lose the resonance. Now, we don't measure these field patterns in our experiment. We do spectroscopy, of course. So we get spectra as a function of wavelength. And the way these show up in the spectra is through these sharp spikes. So here I've labeled a bunch of the first order modes for very high mode numbers. So in this example here, we have all these spikes associated with these different mode numbers for our 4 micron sphere. And if we increase the size of the sphere by 1 nanometer, there's a shift in all the peaks. So now that's what we see in this example. And if we just zoom in on one of these peaks, we see there's a shift of about 0.16 nanometers, which may not seem like a lot, but we could easily resolve that on our spectrograph. So that allows us to basically see changes of about plus minus 1 nanometer with this technique. And same thing for composition, where you can get really tiny changes in refractive index lead to pretty big shifts in these whispering gallery modes, allowing you to study different processes as a result. So a lot of the work that was done by myself, and also, well, when I was with Jonathan Reed and then when I first started my group, was related around studying processes like evaporation and condensation, and also like oxidative aging. So I'll just quickly go through one of these examples just to illustrate the sort of power of this technique for at least this type of situation. So if we consider a situation where you have an aqueous particle, so maleic acid with water, so just two components here, the sort of classic experiment that you would do with the optical tweezers is you just trap it, such a droplet, and then you just hold it at fixed relative humidity to start off. So here it's over 85% RH in the cell. And what you're doing is you're just measuring that Raman spectra and taking out those peak positions and then fitting those using Mie theory to get out the size. And that's what each one of the little black dots would be. And then in this experiment, what you would do is you just jump down the RH every few thousand seconds or 1,000 seconds and see what happens. So that's we're controlling the RH, and then whenever we do that, whenever we drop it down, the size decreases of this droplet as the droplet tries to equilibrate with its surroundings. So it gets drier around it, so it has to shrink down. And that's what we see in this case. So fairly straightforward stuff. And then also you're measuring the refractive index simultaneously, and that's as the maleic acid is becoming more concentrated at lower RHs, so that's increasing, and you see that here. But what's interesting about this experiment, or again, because you have that plus minus 1 nanometer uncertainty, if I just zoom in on a region where the RH is fixed, so the RH isn't changing, and we just look at the radius over time, we see that there's a 40 nanometer drop of the radius over 1,000 seconds. And the reason for this is that the maleic acid itself in this example, it's not completely non-volatile, so it's pretty low volatility, but nevertheless it does evaporate. And whenever that happens, the droplet's no longer in equilibrium, so it also has to lose a tiny bit of water. So because of that, due to that process, we see this slow change in radius over time. And we can actually use this to get out the vapor pressure of maleic acid with this technique, and that's sort of described in some of these papers from like 2014, 2015 era. Again, something you'd never be able to, if you're just using optical imaging like I showed at the very beginning, you would never be able to see, you know, a 40 nanometer size change over 1,000 seconds like that. Just one other thing I want to mention before I get into the sort of real meat of this presentation is that when you're measuring the refractive index, even though up here I just showed it at this is just for one wavelength here, you're actually getting out something called the dispersion as well, and that tells you how it changes as a function of wavelength. So even though we're only measuring our cavity enhanced peaks over a very narrow band, like around 0.65 microns, we can actually use that information to extrapolate out to much shorter and much longer wavelengths, and it provides a pretty accurate description of the refractive index over those wavelengths for a whole bunch of different RHs here. So that'll come up again very soon. So with this type of experiment, you can study, you know, all sorts of different processes related to the atmospheric aerosol. So things like, you know, light scattering is sort of baked into every measurement you take, because you're always, you know, looking at the cavity enhanced Raman spectra, or in some cases elastic light scattering as well. But then other things like I mentioned, heterogeneous chemistry, and then later in the talk I'll talk about phase changes. But then things like surface tension, and then also water transport is a big area of research in this, especially with these high viscosity particles. But I won't be going into that work today. So the two experiments I want to describe today are related to two common questions that people actually have about optical trapping. So, you know, you're trapping this droplet in this focused laser beam, and usually the laser beam's at a pretty high power. So often a new student will wonder, you know, does the particle actually heat up when it's in this trap? And also, does the beam actually stretch the droplet when it's held in this trap? So the answer to both of these questions is yes, and that's what we'll be going through today. We can use both of these to study different, you know, physical parameters. In this case, for the deformation, we can study surface tension, and then for the heating, we can measure absorption cross sections for different compositions. So we'll be looking at that. Now, if you want to do either of these experiments with a classic optical tweezer setup, like I showed at the beginning, the sort of Arthur Ashkin type setup, what you would find is, or the way you'd want to do the experiment is just trap a droplet and change the laser power and see what happens. The problem with that setup that I showed earlier is that there's something called the scattering force that's always pushing the droplet along the axis of propagation of the beam. So as you change the laser power, the droplet actually moves, so it goes up. And eventually the droplet just gets kicked out of the trap. So there's a scattering force. There's also a gradient force that holds it near the focal point. But at high laser powers, the scattering force overpowers that and you lose the droplet. And even if that wasn't a concern of actually losing the droplet, the fact that the droplet's moving around is a major annoyance too with if you want to study either of these effects. So what we did was we just take a second beam and have it counter-propagating against our first beam. And that'll actually cancel out the scattering force, but the gradient force remains. And so we can just trap a droplet and then crank up the laser power and the droplet doesn't go anywhere with this dual beam optical trap. And here's a picture of the very first one we built in our lab a few years ago now, or perhaps even longer, where you just see that we have these two objectives. So these are now long working distance objectives, which is another bonus of this. You're not trapping a droplet right near a slide, which is a hindrance with doing certain experiments with the old setup. So the droplet's just held about 2 centimeters away from either of the walls in this case. And there we can see the droplet's trapped. It's this intense elastic light scattering is just me scattering. So that's not, that's all that is there. So we built this setup and we started to investigate both of these phenomenon. And the first one I'll go through is just the heating experiments. They're a bit more straightforward. So the first system we studied here was just aqueous lithium chloride, just because it's very easy to work with. So what we did was we trapped a droplet and then increased the laser power. And as you can, or what you might intuitively expect would occur actually happens, and that's that as you crank up the laser power, the droplet heats up and you lose water. And so the size decreases, and that's exactly what we see here. So nothing that surprising at this point. But then when you start to lower the laser power back down, so that's the blue dots during the cooling, you see something surprising, and that's that there's this huge power range where you're decreasing the power, yet the size of the droplet doesn't seem to change at all. So there's this hysteresis in increasing and decreasing laser power in the measured radius. So why does this happen? We just basically used a simple Maxwell type equation, his droplet equation, to explain this. So if you just look at the rate of change of the radius, and then each one of our measurements is in a situation where the radius isn't changing. So if you change the laser power, the droplet size will decrease over time, but it happens on the order of milliseconds. And we're taking our measurements in this case like every second or so. So it's always in equilibrium. So we just set that to 0. And then this is modified slightly from the, it's not a pure water droplet, so we incorporate that effect and we get our equilibrium condition over here. And so we can see that there's a dependence on, of course, the saturated vapor pressure, the temperature, and then the water activity, both at infinity and at the surface of the droplet, as you'd expect. And the radius itself is sort of hidden away inside the water activity there, so we don't see that. So with this, we can predict the radius. We just need one other thing, and that's to relate the beam power to the surface tension. I won't go into that, but it's a straightforward connection there. But now you can no longer use me theory. You have to use something called generalized Lorentz me theory for this. So with that model, we then try to simulate our experiment, and it turns out it matches quite well. And we can also understand what's taking place with, or the origin of this hysteresis. So if I just get rid of those data points and look at the droplet during the heating, the size decreases, and at certain specific sizes, the droplet will be sort of commensurate with the trapping laser, so the 532 nanometer laser. Whenever that happens, it can excite, or sorry, the wavelength of the trapping laser will be commensurate with a whispering gallery mode inside the droplet. So it'll excite one of these whispering gallery modes, and there's more light circulating around inside, so it'll heat up. And when that happens during the heating process, there's just this little jump that's quite hard to actually see in the measurements, and then it continues on its way. But when you're cooling, it's a much more distinct effect, because what's happening here is the droplet wants to grow, but it hits one of these whispering gallery modes, so it heats up, so it shrinks back down. And in effect, what happens is it becomes thermally locked in this situation. So we can, do these measurements, and the only free parameter when we're say trying to match the experiment to the model is the imaginary part of the refractive index, which describes the absorption. The K part of the refractive index is very, very tiny for these aqueous droplets. So they're typically referred to as weak absorbers. And you can, if you're not that familiar with the complex refractive index, you can sort of think this dimensionless number here is proportional to the molar absorptivity and the Beer-Lambert law. It's just there's some concentration and then wavelength in there as well if you want to convert them, but nevertheless it's possible. So that's how you can sort of think of this number there, and it's very tiny. So this was our sort of first work on this from 2018, and in the following year we did a whole bunch of measurements across a whole different range of relative humidities for a bunch of atmospherically relevant species. So here, for example, is just aqueous ammonium sulfate, and we've done all these measurements from 85% RH down to just below 40% RH, and just to get out K. And the only drawback of this compared to the refractive index we get out, the real part of the refractive index, which we're always measuring N in our experiments. The only downside to this is we only get K at one wavelength, and that's the trapping laser wavelength, so 532 nanometers. And what we'd like to do is be able to get out the wavelength-dependent imaginary part of the refractive index as well. So there is an approach to this. There's something called the Kramers-Kronig relations. If people have ever done work with infrared spectroscopy, maybe you've come across these. And what these describe, these are just a causal relationship between the real part and imaginary part of the refractive index. And in, I guess, plain English, what they say is, if I know the real part of the refractive index at every wavelength or wave number, as I've said here, I can actually figure out the imaginary part of the refractive index. It's not independent from that. Now, it looks like from our real part of refractive index measurements that I was showing earlier, we do actually have that across a huge range of wavelengths, but it's actually not enough, right? This is going from 0 to infinity. And as you go to very short wavelengths, there's these huge absorption bands that play a key role in determining K. So that's not enough information. However, we do have one other piece of info now, and that's the imaginary part of the refractive index at one fixed wavelength, or 532. So this is, I guess, just summarizing what we have. We have N across the visible region, so from like 400 to 900 nanometers, and K at one wavelength, 532. So we need one other thing, and that's a model for the refractive index. And once we have that model, then we can just plug that in and get out the useful information. So in this paper here from 2019, we outline this model, which is based on the sort of physical origin of the refractive index in these weakly absorbing solutions. And what is the origin? Well, it has to do with strong electronic transitions that take place at UV or higher energies. So here we see some nice measurements from 2011 from this Japanese group, where they're just studying a bunch of aqueous solutions using what they call this like far UV spectroscopy. So you can see that they're taking absorbance measurements way down to below 180 nanometers. And what you find is there's basically, aside from the sodium nitrate example, which has a peak here, all the other ones, there's really not much going on for these, even in this region of the UV, until you get to really, really high energies, and then all of a sudden there's a huge spike in absorbance. So, and then there's all sorts of electronic transitions taking place at these shorter wavelengths. And it's the long tail of those into the visible region that control the refractive index that we see in these weak absorbers. So that's our model for the refractive index. And what we did was we just say, well, there's all these transitions happening at high energy, but we're far away from that region. So we're just going to treat those as being one big transition. And that's why we've called it the effective oscillator model. And then there's so that's it. And with our measurements, we can actually get out now the wavelength dependent imaginary part of the RI, and then also the wavelength dependent real part as well. But so we have that, and then we have these oscillator parameters that we then fit using our measurements. And so this paper from last year describes where we studied a whole bunch of different species. And the real power of this now with this model is that we can then, we're just doing measurements on binary aqueous solutions, so like one salt and water, but we can actually predict, you can have multi-component, all sorts of different species mixed in there, and you can actually get out the wavelength dependent refractive index for those species with this very simple model, because you just have, two parameters in this case describing the real part of the refractive index. And you can do that for any activity because, mass fraction the water, and then the solutes are input parameters. And here's these 20 panels are just comparing a bunch of oscillator model or effective oscillator model predictions to different measurements from our own group, and then also from this pretty ancient JGR paper, and then also the CRC handbook, which, you know, doesn't. The nice thing about the tweezers, which I didn't mention at the beginning, is you can access these metastable states, so you can look at, you know, supersaturated solutions, which you can't do with bulk methods as well. So yeah, the oscillator model works quite well. The problem with this data and a lot of refractive index data out there is it's usually only for one wavelength. So the, you know, Abbe line, 589 nanometers, and we're getting wavelength dependent measurements out from our model, or predictions out from our model, and we'd like to compare those to some measurements. And there's just not that much out there, with one exception, and that's aqueous sodium chloride. So here is just a comparison between the predictions from the model and then some measurements from Cottrell, and then also this older Miller and Seaver paper, and it all matches up pretty well. So we do that, and then we also looked at, say, now solutions with more than just one salt inside of them. So here's magnesium sulfate plus magnesium chloride. So a bunch of different species, or well, 3 different species in there, and it accurately predicts the measurement. We can look at as well organic and inorganic solutions, so that again, in this 1-to-1 molar sucrose to NaCl, we get pretty good matchup with our model. We also looked at some the role that temperature plays in refractive index. And so here we have this example of seawater brine, which has 6 different ions inside of it in this model seawater brine that was used. And there's a temperature dependent composition going from 0 to -35. So again, just applying the oscillator model to this problem, we're able to, with now incorporating a temperature dependence, which turns out to be straightforward. I won't get into it here, but we can accurately predict the measurements in this case. Unfortunately, the measurements here are only at 1 wavelength, but we're predicting the wavelength dependent data as well. So that was seawater brine. If we go back to the atmosphere and look at polar stratospheric clouds, here's some measurements from Uli Krieger's group from 2000, with Thomas Peter, of course, from applied optics, with looking at these sulfuric and nitric acid droplets in their EDB. So this is now, there's wavelength measurements taken at different wavelengths. So here we have measurements going from, you know, room temperature all the way down to almost -60 C in one case. We see that there's a good correspondence between the oscillator model and the measurements in the visible region, at least. But when you start to go to much shorter wavelengths, then there's quite a large discrepancy. And that's probably due to the fact that the model itself is based on the idea that you're, you know, approximating all these high energy transitions as just being one big oscillator. And as you start to get near that region where those transitions actually take place, then that approximation starts to break down. So there's some discrepancy there. All right. So I guess just in the last part of this talk, I want to move on to the other experiment I highlighted at the beginning, which was related to optical deformation. So the idea of using light to deform you know, micron-sized objects has been around for quite a while. In the sort of soft matter physics community, there's this well-known optical stretcher, which can be used to study, in this case, as shown here, phospholipid vesicles. So what's being done in this experiment is they have 2 counter-propagating beams, and they've trapped a vesicle. So this is all in solution, not in air, like we would work with. And at low power, it's spherical, and then when they raise the laser power, you get a deformation. And just from you know what the laser power is, you can just look at the ratio of little m to big M, and then there's a model that they've developed, and you can calculate out the interfacial tension, as they would call it, in this particular system. So this setup here looks a lot like what we're describing with our counter-propagating beams. So if we take this same formalism and apply it to like an aqueous droplets, or in this case, just looking at pure water and air, and predict the deformation for our typical trapping powers, and then even well beyond that, so the very high laser powers. What we find is the amount of deformation for this 5 micron droplet is only about 4 nanometers, even going up to 1 watt of laser power, which is quite a bit. So what's the difference between this setup here, where, you know, you go to high laser powers and you see, you know, deformation on the order of microns, versus ours, where you're only seeing a few nanometers of deformation? It's all about the surface tension. In this system, the water-air surface tension is about 17,000 times higher than the surface tension in this system here. So that means that you get tiny deformations, and unlike this setup, you won't be able to observe the deformation with an optical microscope because it's just too tiny. However, we may suspect that our whispering gallery mode positions will change as you deform this cavity, if it really is this high quality factor cavity. And here's some sort of early calculations I had done with involving T-matrix, just using T-matrix to calculate the extinction spectra for a deformed droplet here. So just this ellipsoid. And we see that with very tiny deformations that you can get not huge shifts, but nevertheless there are shifts in the peak position. So maybe this can work as a way to characterize the surface tension through optical deformation. So again, the basic experiment is you just go into the lab and then change the laser power and see what happens. So here I'm just plotting the whispering gallery mode, the peak positions as a function of laser power now. So we can see as you go from 100 milliwatts, your initial trapping power, all the way up to 1.5 watts, there's these big shifts. Unfortunately, these are mostly due to heating. So that's why you're seeing these huge shifts here. The droplet is just decreasing in size as you're heating it up, which is an effect you'll never be able to get rid of. And it turns out, just sort of back of the envelope calculation shows that it's about 100 times, this shift due to heating versus that due to deformation is about 100 times bigger. So there's not much hope to just sort of subtract that shift from the measurements and then get out the deformation shift. So what the solution to this problem was to look at the particular property of whispering gallery mode, light scattering. And so I guess this is a sort of a very technical slide, but it illustrates the idea behind the measurement I'm going to present in a second. And that's that when you have just a spherical particle, you have these whispering gallery modes circulating around. They all have something called the azimuthal number, and that'll have a certain resonant wavelength, but it's degenerate when it's a homogeneous sphere. So meaning when we observe it on the spectra, they're all at the same wavelength. However, they all actually scatter at over different wavelength ranges. So even though they're all the resonance is all the same, the angular range over which they scatter light changes depending on the azimuthal number, and that's what's shown here. So like this m equals plus minus 59 is scattering over, at least in this plane, over this small angular range, whereas this plus minus 20 is scattering over a much larger angular range. So that's useful. And then the other thing that's useful is that when you deform the sphere into even slightly, you lose the degeneracy, right? Because paths that light takes around the sphere, or the deformed sphere, they're no longer all the same in terms of circumference. So you get different wavelengths for the scattering. So we exploit both of those effects to develop this experiment. And what we do is we have 0 and 90 degrees collection geometry now. So here's our trapped droplet that's being deformed across along this axis. And we collect the 0 degree scattering, or 0 and 180 degree scattering along one axis, and then also the 90 degree scattering here. And then we just compare the two spectra that we measure, and we look at the splitting between the peaks to actually get out the surface tension. That's the basics of this experiment here. And I just want to show the setup just to highlight one sort of technical achievement of it, which is that, so we're collecting the 90 degree scattering and then the 0 degree scattering with two different arms, and then we're simultaneously measuring both of the spectra on the same CCD chip, and that's just to sort of show that we're not like switching back and forth. They're always measured together, and that's how this experiment works. So with both the 90 degree and 0 degree scattering, what you do is now when you raise up the laser power to very high levels, you start to see some splitting between the peaks at these very, very high powers. And if I just zoom in on one area, so just around 900 milliwatts, and I just look at the pixel intensity on the CCD, there is indeed splitting between the peaks, and it matches fairly well with this, again, T-matrix simulation here. So there's hope that we can get out the surface tension. The only problem at this point is that we're working with these high laser powers, and that turns out to be an annoyance for a bunch of technical reasons. So we prefer to work at lower laser powers. And to do that, we use a trick from before with the heating experiments. We just thermally lock the droplets when we do our measurements. So again, we heat them up and then we cool them down into this thermally locked state. And not only does the radius stay fixed, if you just plot this So here's radius as a function of laser power. If you plot the same thing as amplitude of deformation as a function of laser power, you get into this place where you have these large amplitudes of deformation at pretty low laser powers, right? So if I compare this to the bottom point down here to up here at, say, 200 milliwatts, it's about 2.5 more amplitude of deformation up high in that case. So that's what we used. And then once we thermally lock our droplets and take our measurements, we can study the surface tensions of different systems. So here, I guess, for example, just sort of demonstrating the power of the technique, here's aqueous NaCl, and we're, something you'd never be able to measure using a bulk tensiometer at 62% RH, because that would be that corresponds to a supersaturated solution. But with our, contact-free environment in our trapping cell, it won't crystallize. So we can measure the surface tension, again, of these metastable droplets, as demonstrated here. So since developing that, we've done a bunch of different things. One of them is starting to study, we wanted to form core shell droplets, so aqueous core and then organic shell. So these support whispering gallery modes like these animations show, and they move around as you change the shell thickness. The only problem with sort of studying core shell droplets with whispering gallery modes is there's more parameters you need to fit, because you have a shell thickness and then a core thickness, and then also 2 RIs as well. But nevertheless, we've developed, or back in 2015, I had a sort of crude version of the code, and that's been improved. People aren't that interested in the Fortran code for fitting whispering gallery modes, but there it is for anyone that is. So that's just for if it's, again, perfect 2 concentric spheres. When we start to deform it, then that introduces a whole bunch of different problems. But if we just look at this example here, so at low laser power, we have our 2 concentric spheres for 2 different cases. So RA shell is greater than RA core, and then RA shell is less than RA core. So the case on the left is, again, organic shell with aqueous core. And as you start to raise the laser power, it doesn't just stretch, this case on the left, both don't just stretch along the same axis. So the beam would be going left to right in this case. What happens is the shell stretches, but then the core becomes compressed, because you're going from high index to low index, moving from the shell to the core in this case. The case on the right, it's sort of in line with what we'd expect from the homogeneous droplet case. So that's sort of weird behavior. And we had before we actually, started to take measurements on these core shell droplets, the major sort of task is actually, after you have the measurements, interpreting them correctly. So we had to develop a model for, electromagnetic stress on these core shell droplets, and that's described in this PRA paper from last year as well. So here's just both cases showing the stretch and then the resulting deformation for this, and then some actual measurements for after we, or something sort of in parallel to developing this, we started to do some measurements. So here's an example for a droplet that's phase separated at 83% RH, so it's just ammonium sulfate and PEG 1 to 5, and it's just held actually at a very low laser power. And if we just look at the 90° and 0° spectra, we actually have enormous amounts of splitting, so much different than what we were seeing with just single phase droplets here with this coarse shell. So if I just zoom in on one of these peaks, there's quite a lot of splitting in this case. So we have, again, 0° and 9°. So currently we have the model that describes how these are deformed from this paper, but we also need to understand, once it's deformed, how the resonances behave subsequently. And that's what we're currently working on in order to interpret these measurements. But because we have such large splittings in these cases, I'm very hopeful that we'll be able to simultaneously determine the surface tension and then also the interfacial tension between the aqueous core and then the organic shell. So that's where that project currently stands. So just a summary, I went through a few different processes that you can study with atmospheric aerosol. There's all sorts of other things that you can look at as well. And I'd just like to, I guess, right on time. I think you want 40 minutes, so that's what you got. I'd just like to thank my current group members. So Aiden did a lot of the deformation project, and then Allison worked on a lot of the experimental stuff related to refractive index. She's actually going to be leaving shortly to go do a postdoc with Jonathan Reed as well in Bristol. And then Brandon and Alex, I didn't talk about their work today. And then Benjamin has been doing a lot of the modeling of the electromagnetic stress. And then Kyle Gorpeski worked on the deformation project as well. He's currently a postdoc at Los Alamos. And then my collaborator on a lot of this, I think many of you know, is Andreas Zund, and he's great to have him around because he can answer all my naive thermodynamic questions. So just thanks for having me today, and happy to take any questions.
Thanks so much, Thomas. That was really interesting. Maybe I can start with a question while other people are pondering. The effective oscillator model looks really powerful, and it's great. You can use it in a forward direction to predict mixtures. Is there any prospect of using it to work backwards? So take measurements of particles with unknown composition and deduce what they're composed of?
I would say if you had a pretty good initial guess, perhaps, but it's maybe if you had like, you know, good wavelength dependent data, you could do that. But yeah, it would be difficult if it had, you know, as soon as you start to introduce a lot of components to actually, you know, back out what their refractive index was. I don't know. We haven't really looked at that type of problem yet.
Thanks.
I see Arthur's got a question.
Oh, hi, Tom. Yeah, this is really nice talk. So when you're saying that the laser power is heating up, so what's the, like, how much is it heating up in terms of like how many degrees?
Okay, yeah, sorry, I always forget to include this plot and I always get asked this question. So for like an experiment I showed, say here, it's probably only heating up by like say 100 millikelvin. So even when we go to like one,
Okay.
Yeah, it's very small, but nevertheless we can see this size change just because again the vapor pressure has such a strong dependence on temperature, right? That's
yeah, I was curious to see like if you can back out things like the heat of enthalpies of complex organic particles, because that's a big debate in our field too. Is what is that? Because if you go from 30 degrees Celsius to 20 degrees Celsius, how much does the organic evaporate?
Oh, so studying like evaporation rates at different temperatures?
Yeah, not just rates, but yeah, like certainly sort of that shift in equilibrium of vapor pressure. Because if you're basing it on pure components have like maybe 40 kilojoules per mole of delta H of vaporization, but some say it should be like 100. Between 40 and 100, it's actually a big difference in terms of the amount that is formed.
Okay, yeah, I don't know how you would set up that experiment, so it's perhaps.
Okay, thanks.
Hi, Nathan Hilker here. I had a question. So cool work. Could atmospheric aerosol containing, for example, soot be studied with this method? So something that has a relatively high imaginary part of the refractive index, or would heating due to laser absorption be a really big issue?
So if you try to trap strongly absorbing particles with just the standard optical tweezers, what happens is they'll either just vaporize or just be kicked out of the trap. So you can't just trap them like that. However, we have in our group, I didn't describe it today, something called, it's called an optical bottle. It uses a different principle, which is this photophoretic force, where you essentially you have, instead of a focused laser beam, you generate a beam where the core is empty, so there's no light inside, but it's surrounded by very bright light, and that actually pushes strong absorbing particles into the center. So you can trap them with that technique and then do spectroscopy on those. So we've done some experiments with that as well. So it is possible to study strong absorbers with this type of technique, yes.
Oh, cool. I actually had another question, if that's okay.
Yeah, different trap though.
What range of particle sizes can you reliably trap with this method?
Oh, so when you're doing, yeah, for aqueous droplets, like you would just trap with standard optical tweezers, you're usually working like radius like 2 to 5 microns. That's what the typical trapping size is. So of course you can't just, you can't just take a few hundred particle. Well, so you can trap like sub-micron particles with tweezers. The problem is you can't get out much useful information from the once they're trapped, because they won't support whispering gallery modes. They're just too small.
Okay, cool. Thank you.
Hey, Thomas, it's Greg. I got a question. I think you already partially answered it when you answered Arthur's question about the heat in. I was trying to guesstimate the power densities involved, and I gather from the low amounts of heat in it is a relatively low power density. So the milliwatts per kilogram of particle or per liter. I'm not sure if you ever think about it that way. But do you have a sense of what sort of ballpark we're in?
Oh, for the laser power?
No, for the actual amount of energy being absorbed.
Yeah, never. Yeah, it would be very tiny, but yeah, I guess you could convert it with. You could calculate that, but yeah, I've never done that calculation, so yeah, I don't even know what order of magnitude it would be.
Okay, and hence, if you had the core and shell, the idea that the absorbance might be different, slightly different, because Nathan was asking what would happen if you put a highly absorbent one in, but if there's any small differences, it probably doesn't matter in terms of where the.
Oh yeah, the imaginary part of the refractive index, it can just be neglected for like these types of like this. Sorry, I just go to where's like the measurement, like for this type of system here, because they're just both very, again, they're on the order of like 10 to the -9 or 10 to the -8. So it's basically negligible until they get up to like 10 to the -5 or something, like, so they're well below any significant effect. But you can include them in the calculation when you're trying to fit everything. It's just they won't have any effect, except in the case where you're actually measuring the size changes of functional laser power. Then it's significant, or it's the only thing that matters.
Well, thank you. Very neat presentation.
So Thomas, keeping in mind the sort of size range that is accessible from these experiments, is there any prospect of, if you could figure out how to introduce ambient particles into the trap, is it possible you could study ambient particles to understand their morphology?
I would say this is like a sort of general criticism that people often give of like the optical tweezers, that you can't really study ambient particles with it. And I would never argue that it's well suited for that task. Basically, it's good for studying, sort of model systems in a contact-free environment, so you can access, again, these metastable states. That's the main use of it. And then also, I didn't show any of our temperature controlled work here, but now we can control the temperature, so we can supercool droplets as well. That's the main tool of it. And then again, exploiting the sensitivity of the whispering gallery modes, you can, study allows you to come up with new experiments. That's the main appeal of it. But actually taking like ambient aerosol and then trapping them with something like this, or people have done that with like the Bessel beam trap experiments that, Jonathan has done that before, Jonathan Reed. Yeah, but you can do that, but again, the amount of information you're getting out from just using like elastic light scattering at that point, and it's just a really poor way to characterize aerosol particles. There's much better techniques. So you can do it. It's just not a very powerful tool at that point.
And that's because the majority of those types of particles we're interested in are submicron, so it's just not a good fit. Yeah,
they're either submicron, or if they aren't spherical, then they won't support, or they'll be, if they do support whispering gallery modes, they'd have to have very high symmetry to support them, which would be, just a fluke. So you wouldn't get any of those sharp peaks. So you'd just be looking at like the Raman spectra, or just, like elastic light scattering, which again is, I didn't talk about like angular light scattering in this. I've done work on that before, and I'm not a big fan of, characterizing particles with just looking at like, say, 532 nanometer light scattering over different angular range. It just never works that well.
Okay, well, thanks very much for a great talk. Are there any last questions? Okay, if not, thanks so much, Thomas, and take care, and we hope to see you in person one day.
Yeah, thanks for the invite.
Yeah, thank you very much for coming. all the way from McGill, virtually.